case for where the internal force is a function of x, this next example is going to look at where the area is not a function of x. At any location x, we need to define our coordinate system. We're going to define our coordinate system as increasing to the right. So our area is a function of x, but really it boils down to the fact that the diameter is changing. So at any x, we can write a function of x for the diameter such that the diameter is, we need a slope, or what is the change in it? Well, it goes from 2 to 1. That's the amount of, or that's the rise, and the run is over this 48 inches. So the diameter is 2 minus x over 48, or that's the equation for this diameter at any point, and that's in inches. So area is pi over 4 times the diameter squared. So the area A is going to equal pi over 4 times this quantity squared, 2 minus x over 48 quantity squared, and that would be inches squared. Well, what's deformation? Deformation due to this axial load generally is the integral over the length of the load over the area times the modulus dx. Well, we have this function of x as the area, so we have 0 over L P over E times this somewhat cumbersome expression 2 minus x over 48 squared, and all of that times dx. Well, the internal force here is not a function of x. We have an applied 10,000 pounds. We know that our reaction at A is 10,000, and so that internal force anywhere in x is 10,000. We can pull that out of the integral. We also know that the material is the same everywhere. It's a constant, so we can pull that out of the integral. So we're left with 1 over this other stuff. Pi over 4, that's just a constant, times 2 minus x over 48 squared dx. But we said the pi over 4 is a constant, so we can bring that out and flip it over for p over pi e. Things are looking a little better on the integral front. X over 48 quantity squared dx. And at this point, we can seek solace in integral tables. And in the integral tables, we can get ourselves some extra space again. Insert blank page. All right. From integral tables, generally, if you have dx over a plus b x squared, that integral is minus 1 over b times a plus bx. Well, in our case, our A value is 2, and our B value is 1 over 48. So we can say that our deformation is 4p over pi times e times a minus 1 over the b value, 1 over 48. Because the a value is 2, and the b value, our b value is actually minus 148. So we need an extra minus there and a minus here. And that is evaluated from 0 to L. 4p over pi times the modulus, and doing a bit of rearranging, 48 over 2 minus 1 over 48 times L minus 48 over 2. At this point, we substitute our 10,000 pound internal force, our 48 inch overall length, and our modulus of 10 million, and we get that the deformation is 4 times 10,000 over pi times 10 million times 48 over 1 minus 48 over 2, and that ends up being 0.0306 inches. So that's the exact answer from doing the integral, sort of brute force. And sort of an interesting segue into next week's lab, the finite element, and the fact that engineers tend to be lazy, and we don't like doing integrals if we don't have to, is if we look back at this original problem, the fact that it's a tapered bar, we could say, well, what if we just said, instead of this bar that goes from a diameter of 2 inches down to a diameter of 1 inch, what if we said, hey, we can make a guess that it is the same as a straight bar with an average diameter, or 1.5 inch diameter. And you can substitute that into our deformation equation, where the deformation delta is equal to the load times the length over the area times the modulus, and we get a guess of 0.0272 inches. If we compare that over here to what we got from this exact, doing all the integral business, we have 0.272 or 0.03. It's pretty close. Okay, well, what if instead of just 1, we approximated it as a set of 4 decreasing diameter segments that are straight? And if you do that, in fact, with 4 segments, this table shows you what happened. Here, if you say 1 segment that's 1.5 inches, you get 0.272. If you cut it into 2 segments, you get 295. If you cut it into 4, you're already to a 0.0303, and the exact analytic answer is 0.0306. And you see, by the time you cut it into 20 segments, that your approximation using PL over AE terms actually converges on the exact answer. So that is an illustration of the power of finite element, because you're chopping your structure into finite elements that allow you to do easy math and approximate a much more difficult problem.